Quality factor is defined as the ratio of the reactive power in the inductor or the capacitor to the true power in the resistor. Okay, so if we have to mathematically represent this quality factor, this is given as Q to be equal to 2 pi into the maximum energy stored in the inductor or the capacitor divided by the energy that is dissipated per cycle. Okay, energy that is dissipated per cycle. Now, when I consider per cycle, if I'm considering the waveform, per cycle means one cycle will have a duration or a period equal to t. So when I represent the expression for the energy that is dissipated per cycle, I need to also consider the duration, that is the period, equal to t. So let me write the expression for the energy dissipated. In general, we write the expression for the power dissipated P to be equal to I square into R, right? In this case, we are considering the quality factor within the band, okay, within this band. So when it is within this band, what is the value of the current that we have? It is equal to Im by root 2. So this expression will be modified as equivalent to writing Im by root 2 the whole square into R. Now I want the energy dissipated per cycle. So the energy dissipated per cycle will also include the term or the parameter T. So energy dissipated per cycle is equal to Im by root 2 the whole square into R into T, or I can write this as Im square RT divided by 2. Let me name this as equation number 1. Okay, till here it's clear, no? Now we want the maximum amount of energy stored in the inductor or the capacitor, right? So when we write the expression for quality factor, it will not be the same for both of them. So we need to individually compute the quality factor for an inductor and what is the quality factor for a capacitor. So first let me compute for an inductor. So for an inductor, the energy stored in the inductor can be given as the expression half of the inductor into I square. Okay, this is the general expression for the energy stored in the inductor. But if you look at the expression that we want, it is the maximum amount of energy that is stored. So if I'm considering the maximum amount of energy stored, this I will be equal to Im. Okay, and I can name this as equation number 2. So let me substitute these equation 2 and equation 1 in the expression for quality factor. So I have, substituting equation 1 and equation 2, I have Q to be equal to 2 pi into half of L into Im square divided by half into Im square R into T. You can cancel out this Im square Im square half half. So what remains? So you have Q to be equal to 2 pi into L divided by RT. This 1 by T is equivalent to the frequency F, so I can write this as Q to be equal to 2 pi F into L by R. 2 pi F is omega, so I can write this as omega to be equal to Q to be equal to omega L divided by R. So this is the expression for quality factor for the case of the inductor. Now if I am considering at resonance, okay, at resonance, what will happen? This value of omega will be equal to omega naught, and we have seen previously in the derivation for the resonant frequency, omega naught is equal to 1 by root LC. So substituting that, omega naught to be equal to 1 by square root of LC, we have Q to be equal to omega naught L divided by R, that is equal to 1 by square root of LC into L divided by R, or Q is equal to 1 by R square root of L by C. Now generally when we are considering at resonance, the quality factor Q will be denoted as Q naught. Okay, so I can write this as Q naught to be equal to 1 by root L by C, and this Q naught is called as the circuit magnification factor. Circuit magnification factor, that is Q to be equal to Q naught at resonance. Why it is called as the circuit magnification factor, I'll explain later, because we need to finish the expression for capacitor also. So after that together I will explain. But remember, at resonance this quality factor Q is equal to Q naught, and it will be termed as the circuit magnification factor. Fine? Yes? Clear now till here? Yes. Okay. So this is for the case of an inductor. Let us move on to the second part of it. We have only derived for an inductor, we need to derive for the capacitor. So for the capacitor, we have the energy stored in the capacitor to be equal to half of C into V square. Now again coming back to this expression, we want the maximum energy stored. Okay, so when it is maximum energy stored, this is equal to half of C into Vm square. What is Vm? Vm is equal to Im into, what is the reactance? Xc. So substitute this here. So you have the energy stored. Let me represent this as E so that it's easy. E is equal to half into C into Im into Xc the whole square. So let me name this as equation number, what is it? Equation number 3. Now power dissipated equation remains the same. All you have to do is you need to substitute equation 3 and equation 1 in the equation for quality factor. So Q is equal to 2 pi into half into C into, let me write this separately, Im square into Xc square divided by half into Im square into R into T. That is your equation number 1. Okay, so here Im gets cancelled, half gets cancelled, so what remains is that 2 pi into C into Xc square divided by R into T. Again this T you can bring it to the top. This is 2 pi F into C divided by R into, what is Xc square? Since Xc is equal to 1 by 2 pi F into C, I can write this as 2 pi Fc the whole square. Okay. So you have F and 2 pi here, you have F and 2 pi here, so cancel that, C and C gets cancelled, so you get Q to be equal to, these terms gets cancelled, this also gets cancelled, so you have this 2 getting cancelled and you get this as 1 by R into 1 by 2 pi F C. So this can be written as 1 by, what is 2 pi F? It is omega C R. So this is the expression for the quality factor in the case of the capacitor. Okay, now like the way we did it for the inductor, at resonance we found out what is the condition. So similarly let us do the same thing for capacitor. So at resonance you have omega to be equal to omega naught, so you can write this as Q to be equal to Q naught, that is equal to 1 by omega naught C into R. Now since omega naught is equal to 1 by root LC, see what happens, substitute here and see what happens. So you get this as Q naught to be equal to 1 by root LC into C into R. So this goes to the numerator and you have 1 by R, so you can write this as Q naught to be equal to 1 by R square root of L by C. Okay, so one major observation that you can do here is that observe the value of Q naught at resonance for a capacitor and observe it for the inductor. The value of Q naught, okay, that is the circuit magnification factor, will be the same at resonance, whereas it might be different otherwise. Quality factor might be different equation for the inductor and the capacitor separately, but at resonance the expression will be the same. Okay, so you have this Q naught which is equal to the circuit magnification factor and looking at this expression we can say that the value of Q generally will be greater than 1. Okay, now what is this quality factor? We have derived and defined it mathematically, but why do we need to compute this? So quality factor basically gives us the sharpness of the resonance curve. Okay, so if you observe in this case, okay, I have a graph here, right? So I have drawn different frequency responses. So if I'm having a quality factor very high, that means I will be having a response curve something like this, that is shown in yellow color. Okay, so higher the quality factor, better is the frequency response. So write that point as well. Better the resonance or better the frequency response curve. You can see that higher the quality factor, I can say that better is the resonance. Other than this, using the quality factor, you can know what is the selectivity of the series resonant circuit. So quality factor basically gives the selectivity of the series RLC circuit. What is selectivity? I will explain when we come to that topic. But remember this, there is a relationship between the quality factor and the selectivity. So this quality factor gives the selectivity of the series RLC circuit. Now, till now I did specify what is this Q0, that is a circuit magnification factor. So let us look into it in much detail. Till here you're clear, right? Any doubts? Till here is it clear? Yeah, fine. So write the title, circuit magnification factor. Q0. Remember, quality factor and circuit magnification is one and the same, except that we call it as circuit magnification factor because we are finding it at resonance. So to begin this particular explanation also, we need to consider at resonance. Okay, so at resonance for a series RLC circuit, what about the current? The current is the maximum, and this is given by Im to be equal to V by R, and the voltage across the inductor at resonance is given as VL to be equal to, in terms of current and the reactance, I can write this as Im at resonance. So that is Im, the maximum current, multiplied with its reactance, that is XL. Now what is Im? Im is V by R. What is XL? At resonance, this can be written as omega naught into L, because at resonance omega is equal to omega naught, and we know that XL is equal to omega into L, right? So if you look at this particular expression and look at the expression for quality factor, you can see that at resonance we get it as omega naught to be equal to Q0 to be equal to omega naught L by R. So omega naught L by R, that is this part of the expression, can be combined together and written in terms of the circuit magnification factor as Q0 into V. So let me name this as equation number 1. Similarly, you have the voltage across the capacitor at resonance to be given as Vc to be equal to Im into XC. Again Im because we are considering the current at resonance, and this is equal to V by R, and in this case Xc is equal to 1 by omega C, and at resonance this will become omega equal to omega naught. So this is 1 by omega naught C. So if you look at the expression for quality factor, you have omega naught to be equal to 1 by Q naught to be equal to 1 by omega naught into CR. So clubbing this together, this can be again written as Q naught into V, where Q naught is the circuit magnification factor. Now coming to the inference from what we have obtained from equation 1 and equation 2, you can see that at resonance the voltage across the inductor and capacitor is equal to Q naught times the applied voltage. That is because if you look at the series RLC circuit, we represent the applied voltage as V, and you have obtained the expression in this case as Q naught into V. So across the inductor and the capacitor, from equation 1 and 2, we can say it is equivalent to Q naught times the applied voltage. And since the quality factor is greater than 1, or I can say Q naught will be greater than 1, I can say that this voltage across the inductor and the capacitor is magnified by Q times the applied voltage. So hence this term is called as the circuit magnification factor. Clear? Which is very much evident from equation 1 and 2. Is this clear? Everybody? Okay. If it's clear, we'll move into the next one. That is the next set of derivation. That is, you need to show that the resonant frequency is the geometric mean of two half-power frequencies, or obtain the relationship between the resonant frequency and half-power frequencies. Okay. So before you get into this concept, you should know what happens at half-power frequencies. Okay. So just make a note of this before we begin with this particular derivation. Okay. At half-power frequencies, let me draw the response and explain. This is the frequency F0. This is F2. This is F1, and I get the current at this as 1 by root 2 Im. The maximum value of current is Im. So these are my half-power frequencies F1 and F2. Previously we have told that at half-power frequencies the power is equal to half of its maximum value, and the current I is equal to its RMS value, that is Im by root 2. Now how did we get this particular term Im by root 2? Okay. If you look at the expression for current in the case of series RLC circuit, we had obtained this as I to be equal to V divided by R plus J XL minus XC. Correct? If I'm considering only the magnitude part of this particular impedance, where Z is equal to R plus J XL minus XC, the magnitude of this will be equal to square root of R square plus XL minus XC the whole square. So I can write this as I to be equal to V by magnitude of Z. For the current to be equal to its RMS value, that is Im by root 2, you need to have one particular condition to be satisfied. Okay, and the condition is that the impedance or the reactance, okay, the reactance XL minus XC has to be equal to the resistance. So only then you can obtain the current I to be equal to its RMS value. So let's see what happens if the resistance is equal to the total reactance, that is XL minus XC, in the equation star. So if you see this, I can write this as V divided by square root of, if I make R to be equal to XL minus XC the whole square, then I can write this as R square plus R square, right? Yes or no? And this will be equal to V divided by square root of 2R square, or I can write this as V by square root of 2 into R. What is V by R? Corresponding to the maximum value, and this is equal to Im by root 2. So to obtain the current equal to Im by root 2, or the RMS value, the condition that needs to be satisfied is that the resistance should be equal to its total reactance in the series RLC circuit. Clear? Yes. Okay. Now we are looking into the graph where we have the half power frequencies, okay, F1 and F2, and we say that in this region, that is this particular region, the circuit will behave more like a capacitive circuit because XC is greater than XL, and in this region it is the circuit which is behaving more like an inductor, and I can say XL is greater than XC. So if I consider Z1 to be the impedance in this region, okay, in this region, then at frequency F1 I can represent the magnitude of this impedance as square root of R square plus XC minus XL the whole square. The reason why I have written XC first is because XC is greater than XL in this region. Clear? In this region. And because I am having multiple impedances here and here, I can write this as XC1 and XL1. Okay? This is the general expression. Remember, this is the general expression. Now I am considering only this part of the region. So similarly, I can write the impedance for this part of the region, and especially for the frequency F2 as R square plus, now in this case XL is greater than XC, so this becomes XL minus XC the whole square. And since I am considering at a particular frequency F2, I can write this as XL2 and XC2. So this is at frequency F1 and at frequency F2. And another thing to be observed is, since I am considering these frequencies F1 and F2, the impedances especially at F1 and impedance at frequency F2, I can consider them to be equal. That is, the magnitude of Z1 can be considered to be equal to the magnitude of Z2 at half power frequencies. Can you tell me why? Why? What is the relationship between the current, voltage and the impedance? You have I to be equal to V by Z, right? So at half power frequencies, the current is the same. At frequency F1 and F2, current is Im by root 2. The applied voltage is not changing. Then your impedance is Z1 will be equal to the impedance Z2. Clear? Yes. What about others? Has everyone understood? Since the current is the same, current is same in both the cases, okay? At half power frequencies, we have seen from the frequency response curve, current is same, applied voltage is not changing, then Z will also be equal, okay, at F1 and at F2. I am not considering the remaining part. Right now this equation I have written only for F1 and the frequency F2. So I am saying only at frequency F1 and F2 these two impedances are same. Yes. Clear, no?
Yes, ma'am. Yeah, clear, ma'am.
Okay, fine. Okay, moving on to the derivation. You should know these concepts before you step into the derivation. So let's start with the derivation. You need to show that the resonant frequency is the geometric mean of the two half power frequencies, or they might ask you in terms of obtaining the relationship between the resonant frequency and half power frequencies. So let us start. Let F0 be the resonant frequency of the series RLC circuit. So from the response curve, let me denote this as F0, this as F2, this as F1. This current is Im and this current is Im by root 2. So from the response curve at frequency F1 and F2, the output current is equal to Im by root 2, which means the magnitude of the impedances is the same at this point. So let me write the expressions for impedance at frequency F1 to be equal to Z1 equal to square root of R square plus Z1 comes in the lower half, so here XC is greater, so XC1 minus XL1 the whole square, since XC is greater than XL. The impedance at frequency F2 can be given as magnitude Z2 to be equal to square root of R square plus XL2 minus XC2 the whole square, since XL is greater than XC. So let me show that in the graph. XL greater than XC. This is XC greater than XL. Clear? Done till here? Now at frequencies F1 and F2, the current is the same, and hence magnitude of Z1 will be equal to magnitude of Z2. So I can write this as square root of R square plus XC1 minus XL1 the whole square to be equal to square root of R square plus XL2 minus XC2 the whole square. Okay, let me remove the square root and you have it as R square plus XC1 minus XL1 the whole square to be equal to R square plus XL2 minus XC2 the whole square. You can see R is common on both sides. You eliminate that and you get this as XC1 minus XL1 the whole square equal to XL2 minus XC2 the whole square. Again take the square root on both sides. You get it as XC minus XL1 equal to XL2 minus XC2. You have terms in terms of capacitance and in terms of inductance, club them together. So this becomes XC1 plus XC2 equal to XL2 plus XL1. Now in the derivation, what we wanted was a relationship between resonant frequency and half power frequencies, correct? So let me denote this first in terms of omega, that is angular frequencies, because the question can also come say express this in terms of the angular frequencies. Resonant frequency to be equal to the geometric mean of the angular half power frequencies. So it can come in that way also. So let me write this in terms of omega first. Xc is equal to 1 by omega c and XL is equal to omega L. So substitute that here and you get this as 1 by omega 1c plus 1 by omega 2c to be equal to omega 2L plus omega 1L. C is common. This is 1 by omega 1 plus 1 by omega 2, which is equal to L is common, omega 2 plus omega 1. You can still more simplify. Omega 1 plus omega 2, omega 1 omega 2 equal to L into omega 2 plus omega 1. You can cancel out this term here, bring this L to the denominator and take this omega 1 into omega 2 to the numerator, and you have this as 1 by LC to be equal to omega 1 into omega 2. Now if you can recall the expression for omega naught, that is a resonant frequency, at resonance we had omega naught to be equal to 1 by square root of LC. Therefore 1 by LC is equal to omega naught square. So substitute this here. So I can write this as omega naught square to be equal to omega 1 into omega 2, or omega naught is equal to square root of omega 1 into omega 2. So if you see this expression is the angular frequency to be equal to the geometric mean of the angular half power frequencies, but what we desired was in terms of f. So substitute omega equal to 2 pi f. In that case this becomes 2 pi f naught to be equal to 2 pi f1 into 2 pi f2, and this is 2 pi f naught will be equal to, if you see here, this 2 pi common, that is 4 pi square, and I can bring that out and that becomes 2 pi square root of f1 into f2 gets cancelled, f naught is equal to square root of f1 into f2. So finally you have proved that the resonant frequency is the geometric mean of the two half power frequencies. Clear? Is it clear?
Clear.
Okay. So next, I finished another derivation in the other class, so let me do that as well for you. I know it's time. Let me quickly write that, okay? So if it's clear, we'll move to the next one, that is expressions for half power frequencies f1 and f2. So previously what we have done is we have obtained the expression for resonant frequency and the relationship we have shown in terms of the half power frequencies, but now what we want is we want the equation or the expression for f1 and f2. So for this case, let us consider the frequency f0 to be the resonant frequency, okay, and frequency f1 and f2 be the lower and the upper half power frequencies. And we have seen previously that at resonance, at half power frequencies, the equivalent reactance, okay, was equal to the resistance. I have explained that to you in the note. If you remember this note, I have told you if you want to obtain the current to be equal to Im by square root of 2, your resistance should be equal to the equivalent reactance. So that concept we are going to use here. So let me draw the graph once again to show the same concept. I need to consider my frequency f0, half power frequencies f1, f2, the current here to be equal to Im by root 2, maximum value of current is Im, this is f. Now this part is a pure capacitive, so XC greater than XL. This is pure inductive, XL greater than XC, right? So at frequency, I think I made a mistake here. This is f1. So at frequency f1, since XC is greater than XL, I can write the reactance as XC1 minus XL1 to be equal to R. Let me name this as equation number 1. Because here in this region xc is greater than xl, so I have written this as xc1 minus xl1 to be equal to R, because at half power frequencies we say that the reactance is equal to the resistance. Okay. Similarly, at frequency f2, xl is greater than xc, so I can write this as xl2 minus xc2 to be equal to R. So to find frequency f1, that can be obtained by using the equation 1, and the equation for f2 can be obtained using the equation 2. So let us quickly do this. Let me consider the equation 1 first. 1 minute. So considering equation 1, I have xc1 minus xl1 to be equal to R. Let me substitute in terms of omega. This will be 1 by omega 1c minus omega 1 into L equal to R. Take common terms. That is 1 minus omega 1 square CL divided by omega 1C equal to R. Bring this to the numerator. And rearrange this. Now I need an expression in the form of a quadratic equation. So I need to do modifications to this equation so that I obtain a quadratic equation. So first what you can do is you need to multiply this by a negative sign. That is because I need an expression in terms of a square x plus bx plus c. Since there is a negative sign here, so I want to make it positive. So I can write this as minus 1 plus omega 1 square LC plus R omega 1C equal to 0. Okay. Now ax square is there. So let me divide this by LC so that I can still more simplify. So this becomes divide by LC and also rearrange. Okay, rearrange. So this becomes omega 1 square plus omega 1 R divided by L minus 1 by LC equal to 0. Let me name this as equation star. So this equation basically resembles a quadratic equation of the form ax square plus bx plus c equal to 0. And to find the solution of this quadratic equation, we find the solution as equal to minus b plus or minus square root of b square minus 4ac divided by 2a. Okay. Now compare this equation with this and see what is the term a, b and c. So here we have a to be equal to 1, b is equal to r by L, c is equal to, there is a plus here, there is a minus here, So it is equal to minus 1 by LC. And what is X? X is equal to omega 1. So now solve to find out what is omega 1, because we want the expression for frequency F1. So solve. This is omega 1 to be equal to minus of R by L plus or minus square root of B square R by L the whole square minus 4 into AC. A is 1, C is minus 1 by LC divided by 2A. A is 1, so divided by 2. Minus minus becomes plus. This you can bring it to the numerator. So this can be written as omega 1 to be equal to minus R by 2L. 2L because I have brought it to the numerator. Okay, this 2 is there, no? This 2 I have brought it to the numerator, plus or minus 1 by 2 into square root of R by L the whole square. There was a negative sign here, there was a negative sign here, so that becomes plus 4 by LC. Now if you see this term, this is R by 2L and this is R by L. So bring this 1 by 2 inside. Okay, so when you bring this inside, this is equivalent to saying it is 1 by 4. Okay, 1 by 4. So I can write this as minus R by 2L plus or minus square root of 1 by 4 R by L the whole square plus 1 by 4 into 4 by LC. This 4 and this 4 gets cancelled, and if you look at this term and this term, you have R by 2L here. So let me bring this here inside. It becomes minus R by 2L plus or minus now if you see, the expression is having a negative sign here and frequencies cannot be negative. So you can eliminate this negative sign here. So we want the expression in terms of frequency, and we know that omega is equal to 2 pi f. So when you write this in terms of frequency, this 2 pi, bring it to the right hand side. Okay, so I can write this as f1 to be equal to 1 by 2 pi multiplied with the remaining term. So this is the expression for frequency f1. To obtain the frequency f2, what you need to do is consider the equation 2, do the same procedure like the way you have done here, and obtain the frequency f2.